So folks, this is a continuation of the video tutorials that I'm making for a playlist which is intended for doing some very basic and elementary vibration problems using the 3D Experience release 2023X. Now, I have prepared several ones in that playlist before, and more or less they dealt with one particular problem, which is shown down here. It's a mass spring damper system, and in fact, there is one that I did which was called uh, implicit dynamics, where I actually take that same problem, except that the initial displacement, as it is here, it says x of 0 equal to 0. Initial displacement was not 0. X of 0 was equal to, I believe, zero point 0.1 meters or 100 millimeters. Now, uh, I was intending to do that same problem with the modal dynamics procedure that is available in 3D Experience. And I ran into some issues, and this is why I changed the initial displacement to 0 as opposed to the non-zero value that we had before. And I'll come back to that later on as to why that caused a problem. I like to refer to these tutorials that I'm making as killing a fly with a cannon, because this is such a basic problem that has analytical solution, a one-liner solution to this equation, which really doesn't require the use of the finite element package to do that. But the whole purpose is if we can't do these simple problems with the software, then it's unlikely that we can do complicated ones. Now, let me remind you that these tutorials are intended to target the people who perhaps either completely new to 3D experience, or maybe they have some experience with Abacus CAE, and they want to see what the changes are if they want if they want to model same thing in 3D experience. Keep in mind that 3D Experience's platform, its structural FEA solver, is actually the Abacus program, with not all features being either implemented or maybe available in the software. Most are, but not everything. And as you'll see today. In fact, this data that I'm taking is coming from that YouTuber, where the problem under consideration was done with Abacus CAE using uh, using not the modal dynamics, but using the uh, implicit integration, implicit dynamics. Okay? So the difference between this and the other one, and actually the one that I did in 3D Experience with this person's initial displacement is that it's right here. So I'm assuming it's 0. Now these are basic formulas from a third year vibrations class. The natural frequency of the vibration, the damping ratio, and the damp frequency, they're all given here. And the solution subject to these two initial conditions, namely these two actually, the solution is written as a one-liner right here, where the A and B are the constant, and the constant, assuming these conditions, they are equal to the values that are listed here. Okay. And in fact, when you run it, you're going to come across a damped harmonic problem that looks like that. Now remember, this is for 0 displacement. Now, let's go back and see what is it that I was trying to do and what issues that I ran into. I was hoping to be able to solve, instead of x of 0 equal to 0, x of 0 equal to a non-zero value, which is 0.1 meter. Now, I realized that based on the documentation that is available in release 2023X for modal dynamics, something is not implemented as of this date, or maybe I'm not doing it correctly. And here's the situation. When you look at the modal dynamics documentation in online, it says that default initial displacement in modal dynamics is 0. And if the initial displacement is not intended to be 0 and you're trying to use modal dynamics, it should be done in the step previous to that, namely a step which is uh, static perturbation. So it says that if you create a static perturbation step with that non-zero initial displacement implemented, uh, then when the modal dynamics comes later on, it uses that previous implemented initial displacement. And that's exactly, incidentally, that's exactly what I did in the implicit dynamics video tutorial. I first started with a static procedure, stretched the spring by some amount, and then in the second step, which was actually implicit dynamics, I deleted or uh, deleted that initial displacement that appeared in the previous step. So essentially it was stretched, already got what it was supposed to be, and then gave it that initial condition, let it vibrate. And in fact, this is exactly what they're saying. And it says that if you look at the Abacus input file, the line that says star modal dynamics, if the continue is yes, means that it takes the previous result from the perturbation, static perturbation. And if it says no, that is the default, and basically assume that initial displacement is 0. Okay? So to confirm this thing, I went to that input file that's generated, and it's in the background of the 3D experience. You can open it up. It says start modal dynamics, nothing else. And when it says nothing else, it means it's the default, and the default is no. Therefore, the 0 initial condition is used, initial displacement is used. As a matter of fact, when I ran it with 0 initial displacement, means default, didn't do anything, or I specified that the perturbation step, static perturbation step, with an initial translation of 0.1 meter. That 0.1 meter had absolutely no bearing onto the modal dynamics step, and it is not possible to apply translation or translation, non-zero translation in the modal dynamics directly. It won't let you do that. So this is why I had no choice but to say, okay, let's forget about that and let's make that initial displacement equal to 0, so that at least I can show you how it's done using modal dynamics. Now remember, it could be that I'm doing something wrong, or it could be that that step, although it is available in the Abacus CAE, is not implemented in the 3D Experiences platform. Okay, so let's go ahead and do that. I like to see my springs, and therefore I'm going to create 2 points and put the spring between these 2 points. So we go here, one at global origin and another one 40 millimeters away, laid on the y-axis. There we are. And this is the model. That's pretty much it. So now you're going to go to structural model creation, standard automated FEM. All the defaults are taken. Okay. And now you go to in the middle of these tabs, under the abstraction, somewhere in the middle you have point inertia or point mass. You click on it and you select that point here, this point, which is 40 millimeters away, and that's where the mass is going to sit, 2 kilograms. And you can see it looks something like a mass on a scale, or a weight or something like that. Now, next to that tab, there's the connections tab, and to the right of it, on the third one, you have the spring. Third one from the right, you have the spring, and you can do it between a support, a point, and a ground, or you can do it between 2 points. So I'm going to select as the first support this. As for the ground, I'm going to select this other point. If you use the ground here, basically it's just going to be, everything's going to be collapsed into one point. Now, if you zoom in, actually you can see the spring is sitting there. You can see that. We just created it. That's for visual purposes, really. The stiffness of it is 4, according to what the problem said. And we can, this is an axial spring, by the way. And what we can do is we can put the dash bar right now as kind of being parallel to this, so spring dashboard model together. And to do that, you have to check the enable advanced behavior and click on this edit, this pencil. And notice that you cannot select these white boxes, which you should be able to do, but you can select the text. You click on the damping, and it says there's only one option available for you. It says force and moment in the x direction. Now this is not the global x direction, and I suspect it's the x direction of a local x direction along the axis of the spring. Okay, so this value damping was 1, right? And we say okay, and we close it. And this is all we have in our model. Basically, we have a connection, which is a spring, and a point inertia. And all that stuff about nodes and elements and stuff like that is right there. Now, ordinarily, in the past, I've gone to structural model scenario creation, structural scenario creation, but the alternative to this is right here, because there's quite a few things that are available there that is not available in there. For example, explicit dynamics is here, but you cannot reach it there. Anyway, I'm just going to go to mechanical scenario creation. You click on it. Okay, make sure you select the structural to avoid getting stuff about flux and temperature and things like that in the menus. And for finite element model, you have to select it. It's the one that we created, this pool finite element model, which is just two things, a mass and a spring. Now, since this static perturbation step did not work, I'm not going to even bother doing it. First thing I'm going to do is to create a frequency step, because you need the frequency. That's the whole idea behind the natural frequency. The whole idea behind the modal dynamics is first the natural frequencies are extracted. In this case, there's only one natural frequency along the axis of the beam, but it says 10, but that's 10 is default, so it's not going to be able to find 10. There's only one really here, and this is all fine. And now I'm going to apply my restraint. So under the boundary conditions, expand this menu by clicking on the downward black triangle. You select the fixed displacement, you select this point, and you choose all three X, Y, and Z. That's a pin location. And rotations don't matter, because this is an axial spring. Whether you do it or not is totally irrelevant. Then we have another one for this end. This is supposed to move on the x-axis, sorry, y-axis. So x and z are restrained, but y-axis is allowed, is free to move along it. Now, again, these are totally irrelevant for the present problem. Yeah, and that's pretty much it as far as the frequency. I can actually go ahead and run this thing, and I will notice that when I run it, it comes up with one natural frequency of 0.225 hertz. That's this. It'll come up with that, okay, which I'm not going to do. Now, we go and insert a modal, right there, modal dynamics step, right there, modal dynamics step. You you click on it. This other one, we did steady state dynamics. We already did it in a different tutorial. I'm going to put 20 seconds. I want to do the simulation over 20 seconds. And this time increment is really not the same time increment that you're used to in, for example, I don't know, in direct integration. It's not like that. This is just how many points do you want to be, the Duhamel integral to be calculated along the y-axis. We say okay, and let's move on. Yeah, we have to go and ask for, oh, initial velocity, I forgot. So under initial conditions, you click on this initial velocity. You go and select this point. And if you're having a hard time selecting it, you can hide this stuff, it's easier. Along the y-axis and the initial velocity of 0.01 based on the data that's taken from that YouTuber, based on this data, okay? And we say okay, right there. And finally, we go to the simulation. Uh, Simulation, let me show you, by the way, what in the steps that we have here. This is the frequency step. These are the restraint that we put in there, these restraint. This is the modal dynamics step. You don't need to put the restraints because it's already coming from the modes that actually have that restraint in them. All right, so we go to here. You click on the output because you have to ask for additional output, for example, displacement of this point. First of all, we want the history plot because later on I want to plot something versus time. And I'm going to select this point there. The vertex has been selected, and I want a displacement and translations only. In fact, I only need U2, translation U2. But even if you ask for everything, that's fine. And then we say at every increment, we say, okay, that's pretty much it. So let's go ahead and do a model and scenario check. That's fine. And then we do a simulation check. It's a good idea to do these things because if there's anything obvious, it may pop up when you're doing these checks. So we say, okay. There may be some warning messages here, and if you read it, you see that they don't have any bearing on what we are doing. So among other things, for example, I can't extract 10 frequencies because there's only one of them or two of them, whatever, but I'm not going to bother looking at it. Okay, almost done. Good. And finally, this is the simulate. This is where we actually run it. Those were checks. This is just the running stage. With 3DEXPERIENCE, the FEA solver calls it simulate. It'll probably take another minute or so. Okay, there's only one frequency, one natural frequency. And then it does the modal dynamics step. Okay, it's finished. Now notice that just for a second. Frequency step, modal dynamics step. If you click on the frequency step, nothing unusual is going to happen. It just gives you 0.225 hertz, which is exactly what we had here. Okay. Now, if you want to do a modal dynamics step, there's nothing you can see actually, because you want to get a plot of displacement versus time. And even if you clicked on it, you don't get nothing. Okay. So just go ahead and do XY plot from history. And let's see now, we want the translation and we want the second component because that's what we asked for, that's Y direction. And there's the option of modal dynamics, so that's pretty much it. And then say apply. And what you see here is exactly this graph, except that here it's in meters and here it's in millimeters, okay? And that's pretty much it. So we just say okay. And we are done here. Good luck.